Hello guys, welcome to the GC Math Panel Online. In this particular presentation, we are looking at the correction of Advanced Level Technical Mathematics Paper 3, June 2021, question 4. We plead with you to please subscribe to this channel. We are begging that you subscribe and equally invite your classmates and friends to subscribe, share our videos and leave your comments on what you observe or papers you'd like us to answer. If you would like to send any paper to us, you can go to our blog, our website, www.gcemathpanel.blogspot.com, and you send the paper there to us. Now, let us begin. So this particular question was all about studying the function f of x equals ln x plus 1 on x minus 2. So let's see how we study this function. Note that in this particular channel, you have a lot of functions that have been answered, logarithmics and exponential functions. So you can go through our channel and you see many other videos on functions that have been answered. Now let's look at this particular question for 2021 paper 3, question 4. So this is the function. The first thing they wanted us to do was look for the domain of definition of this function. And to get the domain, first of all, ln is not defined for 0 or negative numbers. So whatever we have in this bracket here should be strictly greater than 0. So x minus 1 over x plus 2 should be strictly greater than 0. And secondly, if x minus 1 equals 0, this will give us ln 0, which is undefined. And if x plus 2 equals 0, this will give us x minus 1 divided by that to give us infinity, which is still undefined. Therefore, x should not be equal to 1, and x should not be equal to minus 2. So x should not be equal to minus 2, and x should not be equal to 1. Therefore, means these boundaries are not included. Now, let us get the range of values. Note that since this is an inequality, to get the domain, we'll be looking at solving this inequality for the range of values that satisfy this inequality. So we already know that the boundary solutions are minus 2 and plus 1. What if we could use any of these boundaries, but all of the boundaries cannot be used? So the boundaries are not included. So on the number line, this is what we have. We can now test the region below negative 2, or we start testing from the center. Take any number between minus 2 and plus 1. We can take 0, for example, and test in this inequality here. 0 minus 1 is negative 1, and 0 plus 2 is plus 2. So negative divided by positive is negative, and the negative number is not greater than 0. So this region between negative 2 and plus 1 does not satisfy this inequality. However, if we take any number less than negative 2, for example, negative 3 minus 1 is negative 4, or over negative 3 plus 2, which is negative 1, negative 4 or negative 1 is plus. So this region satisfies, as well as any number greater than 1 will equally satisfy. Therefore, a domain of definition will be the set of all real numbers from negative infinity to negative 2 from below, and from positive 1 from above to positive infinity. We have so many other videos on this channel about this type of functions. So just type GC Math Panel and go through, click on videos and go through all of our videos. You will see the videos on functions. The next part of the question was for us to state the limits at these bounds of the domain of definition. If you need this question paper, just click on the link below and you will find the question paper, or just go to our website and go under Advanced Level Technical Mathematics, and you will find this paper there by just clicking, you download it. So the first limit, as x tends to plus or negative infinity, this limit is going to give us 0. Why, or how do I know this? Now let's look at this ln. What you have in the brackets, the degree of the numerator is equal to the degree of the denominator. That is, you have x to the power 1 as highest degree in the numerator, and x to the power 1 as highest degree in the denominator. So we can approximate this function to just taking the highest degree. So we can write it just as x over x. If it was 2x in the numerator, I'll write 2x over x. If I had a minus 3x in the denominator, I'll write x over minus 3x. So when we cancel out, we'll be left with ln 1. Another way to explain this is, as x tends to infinity, infinity is a very big number. So a very big number minus 1 will not change anything. It's just that very big number. So we can just allow it as just x, as x becomes very large. And with the denominator, as x becomes very large, it will just be approximately x, because a very big number like 100 billion plus 2 will not change anything. It will just be the same 100 billion. That's why we approximate like this, okay? It's on limits. Now, what is the ln of 1? Ln 1 is 0, right? So whenever x tends to positive infinity or negative infinity, the ln of that number is 0. And what does this tell us? This tells us that the line y equals 0 is a horizontal asymptote. So there is a horizontal asymptote existing. For more on these videos, just check on our YouTube page and you'll see a video that gives you the different cases for oblique asymptotes and horizontal asymptote or no asymptote at all. Okay, as x tends to -2 from below, you can just take a number very close to -2. At advanced level, I advise you take a number that is very close to -2 if you're technical. Maybe for commercial students, you can take a number that is a bit far away, but I advise you take a number that is very close to -2 from below. For example, -2.1. We know that -2.1 is less than -2. So I'm taking -2.1 to test here so that I will know the sign of infinity. I already know this limit is infinity because at x equals -2, the function is not defined. Therefore, the limit is infinity. But I need to know if it's positive infinity or negative infinity. So I'm using numbers to test to get the sign. So I take a number slightly less than -2. I'm taking -2.1 and fit into this ln into this function. When I simplify, I'll have ln 31. If the result I have is positive, then the final result is positive infinity, as we can see. So 31 is a positive number, and this gives us positive infinity. Now, as x tends to 1 from above, we'll take a number slightly greater than 1. Of course, you know what, you can guess what we'll take, right? Of course, 1.1. So we fit in 1.1 into the function and test, and we will have negative ln 31, or any other number you have going to be negative ln something. And since this number is negative, and limit is negative infinity, I just added something here in case you were asked in an exam that if you state the vertical asymptotes and the horizontal asymptotes and the center of symmetry, this is what you will do. Of course, you need all these to sketch this function or this curve. So the vertical asymptote, you can see from the domain of definition, x should not be equal to -2. Therefore, the vertical asymptote is the line x equals -2. Then equally, we start x should not be equal to 1. Therefore, another vertical asymptote is the line x equals 1. The horizontal asymptotes, we see it from the limits. From the limits, the limit as x tends to positive or negative infinity to give us the horizontal asymptote. You can start that line is the line y equals 0. And from here, you can get the center of symmetry. If all the limits are infinity, 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 then we know that there is the existence of probably an oblique or slant asymptote. So for the center of symmetry, it is the coordinates of the vertical asymptote and the horizontal asymptote in this case. But since you have two vertical, we'll take the average. So -2 plus 1 divided by 2 gives us -0.5. If we had an oblique asymptote here, we will substitute the value of the vertical asymptote in the oblique asymptote to have the y value at the center of symmetry. You can equally watch the other videos which you have made on this. Now, the next thing in that question is to study the variation of the function. So you have to now look at the derivative. So for logarithmic functions, the derivative is given by the derivative of the core divided by the core. So the core here is x minus 1 on x plus 2. So the derivative of that divided by the x minus 1 over x plus 2. So the derivative of this core, we know that is a rational function. You keep the bottom constant x plus 2. Differentiate the top, you have 1. Now minus the top constant, differentiate the bottom. All that on the bottom squared. Bottom squared is x plus 2, right? But now this is the numerator. All that on the function, all that on the core of the function itself, all that on x minus 1 on x plus 2. So when you simplify at the end, you come out with this function. Okay, this is the result. Now, some students at this point, they'll make a mistake and say that this is strictly greater than 0. No, it's not greater than 0. Be very careful. It will be greater than 0 because the numerator is positive. If the denominator is also positive, then it will be strictly greater than 0. But look at the denominator. You cannot say whether it's positive or negative. It will be positive depending on the value of x and negative depending on the value of x. So since the numerator is constant, which is positive, you're not interested in that for the sign. You're interested in the denominator whose sign will keep on changing. So you can also that since the numerator has no x, there is no variable to solve for in the numerator. It means there is no turning point. We can now move on to make a variation table. So for a variation table, we have from negative infinity to minus to -2 to 1 and positive infinity. Why? These are the values that you see on the domain of definition. Okay. If there were turning points equally, we include the x values here, but there are none. Now, -2 and +1 are vertical asymptotes. So you're going to indicate those with solid lines, as you can see. And we can now move ahead to start looking at the sign of the function. That's the monotonicity, whether it's increasing or decreasing. Now we take any number between negative infinity and negative 2, and take negative 3 and test in the gradient function or the derivative. So if you take negative 3 here, numerator is already positive. Now let's look at the denominator. Negative 3 minus 2, negative 5, into negative 3 plus 1 is positive, right? Negative times positive is negative, and positive divided by negative is negative. Therefore, we see here that the function is decreasing in this interval. Now, in the interval between negative 2 and 1, this is another place where students will make a mistake. If you look at the domain of definition, the function is not defined in the interval, the x interval from negative 2 to 1. Let's take any number and test. Let's take 0, for example, and fit in this function. You have ln 0 minus 1 is negative 1 on 0 plus 2 is 2. So the ln of negative we have does not exist. So in this region, the function does not exist, okay? So now the region above, if we test using a number greater than 1 in this function, let's take 3 for example, or 2 for example. No, 2 will not be a very good idea, right? Okay, so let's take 3 and test. If you fit 3 here, the 3 minus 2 is positive, and equally you have 3 plus 1, which is positive, right? Okay, yeah. All right, so you realize that you take a number between negative infinity and negative 2. Let's fit here and see. So we have negative infinity. Let's take negative 3. Negative 3 plus 2 is negative 5. Into negative 3 plus 1 is negative 1. Negative times negative is positive. In fact, it's going to be positive. And if you take another number greater than 1 for this interval, 2 or 3, for example, if you have 3 minus 2 is positive, 3 plus 1 is, so everything is positive. Another thing we need to notice that, so in this region, the function is increasing from 0 as x tends to negative infinity, y tends to 0 as we saw from limits. And as x tends to 2, negative 2, y tends to positive infinity as we equally saw from limits. And then for the region from 1 to positive infinity, it is equally increasing. As x tends to 1 from above, we had negative infinity. And as x tends to positive infinity, we had 0, just like here. So we have negative infinity at this point. But with the region between -2 and +1, the curve does not exist. So we share this region. You can equally see this in the domain of definition. The function does not exist in the region or in the range from -2 to 1 for the x values. So one remark, this curve does not cross the x, cross the x-axis, and the horizontal asymptote. So it does not exist in this interval from -2 to 1. Okay. So the domain will be different if we change these brackets that we have here. If we change these brackets that we have, and we use something else, let's say absolute values, to get the domain, we have to follow different procedures. You can usually see that in our videos. So after this step, we're being asked to sketch the curve of this function, and they give some instructions on, I think, the scale. Here, I've not really followed the scale because of space and to explain, but you have to follow the scale and the space in the exam. So we start by looking at the horizontal asymptote is the line y equals 0. You can see it in yellow. And it's broken lines because it's an asymptotic line. Then we have one of the first vertical asymptote x equals 1. Then we have the vertical asymptote x equals -2. Now, the curve increases below -2. That's from x equals -2. Increases from this point to positive infinity. Can we see? So the limit as x tends to 0 to -2 from below was positive infinity. And as x tends to negative infinity, what did you have? You had 0. So it was almost approaching y value of 0. So that's why this point is here. We link this. Then equally, as x tends to 1 from above, we had negative infinity. This is it. And then increases, does not cross the horizontal asymptote. So it should be somewhere now around here. We now link these 2 points, link this one, and link this other one. So this is the curve of this function that we have been asked to sketch. Guys, please don't forget to subscribe and to share this video and leave your comments. The way you can encourage us to make more videos for you is by subscribing, leaving your comments, and asking us or making requests for us to answer a particular year. We plead on you that if you have past questions or past papers, you can send to us directly from the blog or by email. You can see our WhatsApp number from the blog address www.gcemathspanel.blogspot.com, and from there, you can actually send us the paper in PDF directly. You can send us the paper directly in PDF. So you can equally comment. We click on your blog, you see the remaining questions or the remaining papers. Just go to our blog. This is the blog address www.gcemathspanel.blogspot.com. Here equally we have a lot of past questions, past papers that you can actually use to better your studies. Please visit this blog and you will not regret visiting it. Thank you so much and God bless you in your studies. Bye-bye.